what are the fundamental quantities? One, length. And remember we said you use big L. But because length is measured in meters in the SI units, if you simply use the meter, it is understood. What is the next one? 2, mass. The mass we use big M, but since mass is measured in kilograms, we can accept the kilogram. So meter is the unit for length, kilogram the unit for what? Mass. And the third one, we said we have 7, but we just single out only 3 of them, and we are dealing with only the 3. So this is time, and time we use T, and we said time is measured in what? Seconds. So we are saying that these are the fundamental quantities. Right? Okay. From here, we said that any combination of these, we call it what? Derived quantity. So a derived quantity is simply a combination of these or a repetition of any one of them. It's a derived quantity. An example is speed. What is speed? Speed is simply distance divided by what? Time. But remember, this is only valid when there is no what? Acceleration. I don't want you to go and write this equation and use it and solve a problem and come out to say that I said speed is equal to distance over time. By definition, that is true, but where there is acceleration, this equation is not valid. Okay, so based on this, let's just do our dimensions. This is measured in what? So in actual fact, if we are using the dimensional analysis, this should be L divided by what? T. Distance is length, time is T, right? But in terms of units, it's going to be what? Meter divided by what? Second. So that is why speed is often recorded in what? Meters per second. Right? Let's do another example of dimensional analysis. Acceleration. Now you have become masters of physics. You now know all the equations, so you should be able to play with them. What is acceleration? We said it's change in velocity divided by change in time, right? Now, this can be written as what? Change in velocity times 1 over time. I'm just doing this so that the units will come out clearly. This is the same as that, correct? Okay. Change in velocity will have the same units as speed, right? Meters per second. So this portion here would be meters over second. Times. Change in time will have units of what? Seconds. So see that I have 1 over second. Now if you evaluate this, m times 1 is equal to what? M. S times s is equal to what? S squared. So that's why acceleration has units of what? Meters per second squared. Yes?
Yeah, the acceleration is equal to delta V divided by delta T, right?
Mm-hmm.
It's also equal to V average divided by T.
Correct.
So you mean delta V divided by delta T is equal to V average divided by delta T?
No.
Which is
what you are trying to say is this. Average velocity times time, that's what you are trying to say. It's not acceleration, it's distance.
No, average velocity divided by time.
Sure. So he's saying this acceleration is equal to average velocity divided by time. That is correct.
So you mean that average velocity divided by time is equal to delta V divided by delta T?
Correct. In terms of
How's
units.
that work? I mean, it's not the same.
It's the same in terms of units.
No, I'm not talking about in terms of units.
Yeah.
I'm talking about, like in math, it's not gonna be the same. Because V average is V1 plus V2 divided by 2.
Yes.
Delta V, it's V final minus V initial.
Okay, here, let's not mix up issues here. Right now, we are just dealing with what? Dimensional analysis. So let's clear the dimensional analysis for everybody to be okay. And then when we get to the other portion of using the equations, we take that. Because otherwise, people will get lost. Is that okay? Okay. So in terms of dimensional analysis, this is equally correct. Because this is going to be, V here will be meters over second, then times 1 over second. You see that the units are the same. So this is correct. But in terms of what you are saying, it's likely not to be correct. It may be depending on the situation, but I don't want to go to that for now. When we get there, bring it up. Is this okay for everybody? Okay. So we are done with dimensional analysis, but we had a reason why we are doing all this. And the reason was that we use it to check the correctness of what? Equations. Because dimensions you can operate them like what? Like operators. Multiplication, division, addition. It should work. But at the end of the day, what we are saying that the units on the left-hand side must agree with the units on the what? Right-hand side for an equation to be valid. Not only an equation, for an operation to be valid. If the units are not the same, then that operation or that equation is not valid. Don't use it. The only shortcoming of dimensional analysis is that it does not cater for what? Multipliers. Right? Let's do an example. V is equals to V naught. You already know this equation. Right? V is final velocity. V naught is what? Initial velocity. A is what? Acceleration. And T is what? Time. We want to find out if this equation is valid dimensionally. So you start. This one is what? Meter over second equal. This one will also be what? Meter over second plus, we already know what acceleration is. It's meter over second squared times second. So let's check. Are the units the same? Do you see that this second will go with one of the seconds here? So if this goes with this, now you count. Meter over second, meter over second, meter over second. So the operation is valid, or the equation is valid. Right? Because even if you add this to this, you are going to get what? 2m over what? S. But we are saying that dimensional analysis does not cater for what? For multipliers. So that 2 is of no use to us. Right? Try this by yourselves. V is equals to V squared plus AT squared. Check it out and see, is this a valid equation or not? Is it valid? No. Why is it not? Let's try it. What is here? Meter over second equal, what is here? Meter over second all squared plus, this is what? Meter over second squared, second squared. It's truly this. You don't even need to go further, right? this is not valid. So remember to do this if you are ever asked. Okay, the next one we want to remember is frequency. What is frequency? We define frequency as equals to the number of events divided by what? The time. But the time should be in seconds, so that we will call that hertz. So let's say I go to and fro 10 times, and within that 10 times, I did it in 4 seconds. So I divide this by 4 seconds, and this will be my frequency. So frequency is always the number of events divided by what? The time. And so here you will see that you have 10 over 4 times 1 over second. And 1 over second by our definition is called the hertz. So this is, okay. From frequency we learned period. What is period? We said it was simply the inverse of what? Frequency. So that means T here is equals to 1 over F, which is simply equals the time divided by what? The number of events. You see that this would have been 4 seconds divided by what? 10. You see that this would be 2 over 5 seconds. So that's the thing you should remember. Okay, at this point we need to know what a vector quantity is and what a scalar quantity is. A scalar quantity is that which has only what? Magnitude. That is, it has just the number. But a vector quantity is that which has both magnitude and what? Direction. And you should be able to give examples. Time is a scalar quantity. Mass is a scalar quantity. Velocity is a what? A vector quantity. Acceleration is a vector quantity. Weight is a vector quantity because it is always what? Acting vertically downwards. So these are typical examples that you need to remember. Okay, at this point, any questions? Do you have any examples we can look at? Otherwise, we can move on.
Chapter 1?
Yeah, if you have a problem in chapter 1 or something related to that, you can bring that. But if you are comfortable, we just move on. We move on? Sure. Okay. Now, we will look at the Newton's equations of motion, and that is where your question could now come up. And I will write the equations and make sure that you go with them and understand. So the first one is acceleration. We define acceleration as change in velocity divided by change in what? Time. That is the definition for acceleration. There must always be a change in what? Velocity divided by time before you define it as acceleration. And we said this was equal to what? Final minus initial divided by time. So I can rewrite this as V naught divided by T. This is the equation we have. So what is this? Final? What is this? Initial. And what is this? Time. Okay. So from here we said that if the object starts from rest, what does that mean to us? It means V initial is what? 0. What if the object comes to a halt or comes to a stop? What does that mean?
0.
It means V final is what? 0. So know when to use them. Okay. The other one is if you are told that the object moves with constant or uniform velocity, what does that mean? It simply means that your V final is equal to your what? V initial. And if V final is equal to V initial, then this minus this will be equal to what? 0. So an object moving with uniform velocity is not accelerating, as far as this is concerned. The only time you will begin to look at and say, well,